Today, we are writing Python code that reaches out of the screen and controls the physical world, starting with a smart LED controller. You do not need to buy any equipment or install complicated software to follow along. We are going to build and test everything using a free browser-based simulator. Our hardware platform for this project is the Raspberry Pi. This board is packed with an array of pins designed specifically to receive digital instructions. By writing logic in a virtual environment, anyone can test and perfect their circuits for free. This approach removes the financial barriers to entry, giving you a direct, accessible path to learning robotics and automation. Step 1 is setting up our workspace. Navigate to wokwi.com and select a new Raspberry Pi Pico project. On the virtual board, our LED is wired directly to pin 5. This is the physical connection our code needs to target. By default, a computer or a microcontroller does not inherently understand how to send power to those physical components. To solve this, we use libraries. Think of a library as a pre-written instruction manual that teaches your Python script exactly how to communicate with the hardware. In your editor, type from machine import pin. Ensure the P is capitalized or the system rejects it. Next, type from time import sleep. Without this, our LED toggles too quickly for the human eye to process. With these two manuals imported, our script now has the specific vocabulary required to bridge digital logic with real-world electrical actions. Now that the board can operate its pins, we need to give our LED connection a clear label so we can reference it easily. To do this, we use a variable. Think of it as a container, much like a lunchbox. Let's create ours. Type LED equals pin 5 pin.out. The number 5 maps directly to the physical wire connection we looked at earlier. The pin.out command dictates the direction of the electricity. We are sending an electrical signal out to turn on the LED rather than receiving data in. By defining this variable, we create a human-readable map. Every time we type LED, the code knows exactly where to send the voltage. If we tell the LED to turn on right now, the program will execute that single instruction and immediately shut down. We need continuous action. To keep the device running forever, we set up an infinite loop by typing while true. Watch your case sensitivity on the capital T. Press Enter. Your cursor is now indented. Python requires all commands inside the loop to be pushed in by a tab space so it knows they belong together. Let's light it up. Type led.value1. In binary, 1 means on, sending power through the circuit. To keep it on, type sleep1 to pause for 1 second, then cut the power with led.value0 and add a final sleep1 before the loop repeats. Your code is complete. Hit the Run button in the simulator to execute the script. This continuous cycle of high and low electrical signals within an infinite loop is the foundational operating logic running millions of automated IoT devices today. Look at the preview window. You should now see your virtual LED steadily blinking on and off every second. The Python syntax you just wrote operates at a massive scale. It is the exact same language used to run global tech platforms like Instagram. Now that you have a working circuit, try testing the limits of your logic. Change the values in your sleep functions from 1 to 0.2 and run it again to observe the difference. You have successfully written digital instructions to control physical hardware. By toggling this single pin between two states, you've applied the exact signaling mechanism used to trigger everything from motor controllers to digital displays.